Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. It really helps us grow our channel and bring you more free content. So a colleague, Professor Coynes, did this really interesting integral, and he used this integral to be able to integrate e to the negative x squared dx, which is, the Gaussian curve, or, the probability curve. So he showed that, going from rectangular form to polar form, we got this. And he also explained that this r comes from the Jacobian of this transformation. Since I just did a video on multiple substitutions, let's prove that this is the Jacobian. In the second half of the video, what I want to do is I want to do another integral for a multiple substitution that has a much more interesting region. So let's prove that this is the Jacobian. So we know that our substitution x is going to be equal to r cosine theta, and then y is going to be equal to r sine theta. Now, in the previous, we talked about the Jacobian of u comma v being equal to, well, the first column is going to be your dx's, and the first row, and then your second row is going to be equal to your dy's. Now, the first column are going to be the derivatives with respect to your u's, and then the second column are going to be the derivatives with respect to the v's. Now, when I want to do the Jacobian of r comma theta, well, very similar. This is going to be equal to the determinant of, well, I'm going to need my dx's for the first row and my dy's for my second row. Now, the first column is going to be the derivatives with respect to the first variable, which is going to be r, so this is going to be dr. And the second column is going to be with respect to your theta, so this is d theta. So let's find the partial derivatives. So the derivative of x with respect to r is going to be equal to, well, cosine of theta is a constant, and the derivative of r is just 1, so it's going to be cosine of theta. And then the derivative of x with respect to theta, well, r is a constant, so leaving r there. Derivative of cosine is negative sine of theta. Now, the derivative of y with respect to r is going to be equal to the sine of theta, and the derivative of y with respect to theta is going to be r cosine of theta. Now, multiplying these diagonals, we're going to have cosine times r cosine, so this is r cosine squared of theta, minus the multiplication of this diagonal, which is going to be minus r sine times sine, which is going to be sine squared of theta. So this is r cosine squared theta plus r sine squared theta. Factoring out your r, we're going to have cosine squared of theta plus sine squared of theta. And we know that that is the Pythagorean theorem, which gives us 1, so this is going to be equal to r. Now, with your multiple substitutions, we know that we technically are going to need the magnitude of the Jacobian, so we're really going to need the magnitude of r. And since r tends to be, running from 0 to whatever, the magnitude of r is just r, and that's why, that is the Jacobian of that transformation. All right, let's show one more example that has a more interesting region than the video I did to set up multiple integrals. All right, so here's our example. What I want to do is I want to integrate from 0 to 1 of the integral from 0 to 1 minus x of the quantity, the square root of, the square root of the quantity x plus y times the quantity y minus 2x squared dy dx. So we know in order to make substitutions, well, actually, let's not even talk about substitutions first. That is not integrable as it sits because there is no just simple u to where I'm going to get a du to recover in this expression. So multiple substitution is really helpful because then I can make this in terms of, a separable equation. So, and you'll see what I mean separable here. So if I make u is equal to x plus y and then v is equal to y minus 2x, what I'm going to have here is going to be the double integral of, root u times v squared, du dv or dv du, depending on how I want to set this up. But now if I'm going to, say this is dv du, then this is just a constant. I just integrate this at its evaluations, and then I can go after the u. So now that thing would be integrable as it sits. Now, in order to set up the integration, I can't just substitute for the integrand. I also have to substitute for the region, and the region is just as important. So let's go after that. So what I know is that x's are bounded between 0 less than or equal to x less than or equal to 1, and the y's are going to be 0 less than or equal to y less than or equal to 1 minus x. Now, graphing this thing, you know, what does the region R look like? Again, it's not necessary to graph it. We really just have to transform it. But I like to look at it so we can see what happens, and something neat, you know, kind of comes out. So what I know is x is equal to 0 would be, you know, this vertical line, and then x is equal to 1 is going to be this vertical line. And then y is equal to 0 is going to be this horizontal line. And then y equals 1 minus x is going to have a y-intercept of 1 and a slope of 1. And it's going to run right into that exact same spot right there. So it's interesting when we do this integration, we can see, you know, using that vertical scalar bar here that it slides from 0 to 1, and then, you know, the min or the lower bound is going to be at 0, and the upper is going to be at this 1 minus x. So it really doesn't look like this, you know, this second piece, pink piece is going to be needed because of that intersection stops there anyway. Now, when we take this to the new region G, something similar is actually going to show itself, so it's kind of cool to look at. All right, so in order to do that, we're going to have, you know, I have x is equal to 0, I have x is equal to 1, I'm going to have y is equal to 0, and I'm going to have y is equal to 1 minus x. So in order to do these, I'm going to have to solve our substitutions for x and y using a system of equations. So let's choose, I like to choose the right-hand side and pick the easiest variable, so I'm going to solve for y. So v minus 2x is equal to y, and now I'm going to plug this into here for our y. So u is equal to x plus v minus 2x. What I'm trying to do is I'm trying to write x and y in terms of u and v instead of u and v in terms of x and y. I'm trying to switch this, and all it is a system of equations. So over here, I've basically done that. I have x in terms of u and v, so I just have to isolate x. So this is a plus. This is a plus. So x plus 2x is going to be 3x and then minus the v, so u minus v is going to be equal to 3x. So then x is going to be equal to u minus v over 3. And then similarly, I can plug this into here and I'll have y in terms of u and v. So v plus 2 times x, which is going to be u minus v over 3, is equal to y. And then simplifying, I'm going to have v plus 2u over 3 minus 2v over 3 is equal to y. And I can see this is the same thing as 3v over 3, so 3v minus 2v is going to be equal to v. So I'm going to have 2u over 3 plus 1v over 3 is equal to y, or y is going to be equal to 2u plus v all over 3. Now I can, now I can plug these things in. So x is going to be equal to u minus v over 3 is equal to 0. Multiplying both sides by 3, so u is going to be, well, u minus v is equal to 0. So u is equal to v, or I tend to like to write v in terms of u. Because remember, this is the x-axis, this is the y-axis. So we tend to like to solve things for y when we can, but sometimes, sometimes we can't, because this is going to be the u and this is going to be the v. So, horizontal axis, vertical axis, which is why I like to solve it that way. Now, similarly, x is equal to 1, so u minus v over 3 is equal to 1. Multiplying both sides by 3, we're going to have this. Now I can interchange the v and the 3, so u minus 3 is equal to v, or v is equal to u minus 3. Now y is equal to 0, we're going to do this substitution, so 2u plus v over 3 is equal to 0. So multiplying everything by 3, 2u plus v is equal to 0. So v is going to be equal to, sending the v, let's send the 2 over, so v is going to be equal to minus 2u. And then similarly, for y, we have 2u plus v over 3 is equal to 1 minus x. Now x is going to be equal to u minus v over 3. Multiplying everything by 3, 2u plus v, don't forget that one too, 3. Minus, now when you multiply by 3, this 3 is going to go away, but this negative is still going to distribute, so minus u plus v. Now notice over here that these v's are going to go away, so those have the same sign, so they're going to cancel. So sending the u over, we're going to have 3u is equal to 3, or u is equal to 1. So sometimes, again, you're going to get vertical lines every now and then. All right, so graphing these. U is equal to v is going to be this. U is equal to v minus 3 is going to be, 3 units below it. This. v is equal to negative 2u. And then u is equal to 1, and what's interesting is this u is equal to 1 is actually going to run right into this intersection right here. So it's going to look just like this. So just like, this pink line isn't needed here, you can kind of tell that that pink line's not needed there because, just like this is the region of integration, over here, this is our region of integration. So this triangular region is conserved to this triangular region. So when I integrate this thing, I'm going to have to use, a vertical scanner bar without the mess. Let's kind of get some of that out of there. So what I can see is this is, this scanner bar is going to slide from 0 to, this is 1. So this is going to go from 0 to 1. And then this bottom curve, this lower dot is going to be that lower bound, which is going to be equal to this v is equal to negative 2u. And to this upper curve right here, which is v is equal to u. All right, so now setting up our integrations, or, with the substitution. So this is now going to be equal to the integral, but into the Jacobian. Let's get that. So the Jacobian of u comma v is going to be, remember, this is going to be dx du, this is going to be dx dv, this is going to be dy du, this is dy dv, x's, y's, u's, v's. So the derivative with respect to u is going to be a third. The derivative with respect to v is going to be negative a third. Now for the y's, the derivative with respect to u is going to be 2/3. The derivative with respect to v is going to be 1/3. So multiplying these diagonals, 1/3 times 1/3 is going to be 1/9. Minus a minus, so plus 2/9. So this is going to be equal to 3/9 or a third. Now we still have to take its magnitude, but the absolute value of a third is still a third. So remember that we still have to find the magnitude of that thing. All right, so this is going to be equal to the integral from, well, we know it's going to go from 0 to 1. It's sliding this way, so 0 to 1. And that is going to be in the u direction. And then this is going to be the integral for our v's is going to go from this lower bound, which is negative 2u, to this upper bound, which is going to be u. So minus 2u to u, and that's going to be in the v's. I have to multiply by the Jacobian, and then with the magnitude of it, and then this, now plug in our substitutions, this is going to be the square root of x plus y, which is going to be u, multiplied by v squared. Now I can pull out the 1/3, and then I can integrate this, the v first. So this is going to be root u, this is going to be v cubed over 3, evaluated from minus 2u to u dv. So doing that evaluation, we're going to have 1/3 of the integral from 0 to 1 of root u times, evaluating at the top, this is going to be u cubed over 3 minus the bottom, this is going to be a minus 2u cubed over 3 dv. Now without writing this thing a bunch of times, let's kind of investigate this simplification. So negative 2u cubed is going to be, negative 2 times negative 2 times negative 2, which is going to be negative 8u cubed. So this is going to simplify to minus 8u cubed. Now minus a minus 8 is going to become 9u. Now this is going to be positive 8u cubed. So u cubed plus 8u cubed is going to be 9u cubed over 3. So this entire thing is going to be 9u cubed over 3, which is going to be the same thing as 3u cubed. Now the 3's are going to cancel out here. So this is going to be equal to the integral from 0 to 1 of the square root of u multiplied by u cubed du. Now adding their powers, so then I can integrate. This is going to be the integral from 0 to 1. Well, 1/2 plus 3 is going to be 3.5 or 7/2. So this is the integral of u to the 7/2 du, which is going to be 2/9 u to the 9/2, evaluated from 0 to 1. So 2 over 9 times 1 to the 9/2 minus 2 over 9 times 0 to the 9/2 is going to finally become 2 over 9. So again, If you like our content, please consider liking, subscribing, and sharing. It really helps us grow the channel. Thank you.